Hello and welcome. I will be talking to you about AI in the fast lane, how we can use smart traffic systems to unclog our cities. This way, we can use intelligent technology to revolutionize urban transport. First, a couple of things about me. My name is Avraam Tolmidis. I have been working as an engineering manager for the last 7 years. I have worked in various technical roles for the last 13 years in the automotive, fintech, and tech industries. I have worked for years in automated driving, and I have an electrical and computer engineering degree, a PhD in the field with focus on multi-objective optimization, and I have a degree in education. Throughout my career, I have been mentoring and trying to grow professionally computer engineers. And fun fact, before switching to the industry, I was working as a teacher. I was teaching for 7 years. But let's look into more detail and what we will be discussing today. First, I will touch a bit on what the current challenges are in traffic management systems. Then I will discuss a bit how we can use software agents and smart traffic systems. Then I will touch briefly on what the required infrastructure would be to be able to implement such a system. And finally, I will present what the benefits can be of using AI-driven traffic management. Let's get started then. So, what are the challenges? I'm sure everyone has faced, if not all of them, most of them, and everyone is familiar with them. First, we do have an increasing congestion. Yeah, congestion is rising in urban areas. We have cities being overpopulated, population is growing, and this also leads to the increase in vehicle usages, and this leads to longer commute times and yes, the infrastructure in our cities is often inadequate. This can happen either because it's outdated and it hasn't been maintained for some time, or because it was not built to withstand all the pressure it feels now with all the vehicles and all the road users that increase in number. I already mentioned that we have a growing number of vehicles. This doesn't happen with the same rate in every country in the world or every city in the world, but the trend is still increasing. And this poses significant challenges to the traffic management systems. All this also generates the other problem when we have traffic events. Usually our reaction is delayed. Our systems are too slow. Usually some human needs to detect something and some human needs to intervene, and that can take a lot of time. So the result is lost time, lost fuel or other type of cost, and most importantly, lost lives. But what if we didn't have to have such a traffic management system? What if every car and traffic light was an intelligent agent? What if they could negotiate, adapt, and optimize their behavior in real time? That is the idea behind the decentralized traffic intelligence. Let's look into it a bit more. How would we use software agents in a smart traffic system? There would be mobile agents that would correspond to the vehicles. And then in the intersections, we would have stationary agents. Each of them makes decisions based on local context mostly. However, if we feel that there's a need for that, we can use more centralized optimizations and more centralized policies so that we can try to optimize for the broader urban area, not just locally. And this is the AMOR system, which stands for Adaptive Multi-Objective Optimized Routing. Agents optimize for time, distance, cost, emissions, or any other objective that one might think makes sense. The agents bid for road segments based on current values of these objectives, and the routes evolve continuously as the traffic changes. So, in more detail, a vehicle approaches a decision point, like an intersection. It requests a potential next step from the nearby stationary agents. Each stationary agent calculates a bid, a cost estimate, for using the road segments of a route it proposes for the vehicle to take based on the current data. Then the vehicle evaluates all bid using its weighted objective function, and it selects the lowest cost next step, which is the best trade-off among the priorities we have selected to optimize by. How is the bid negotiation happening? The vehicle agent sends the route request to the nearby stationary agents, plus the weights for each objective to optimize. The stationary agent then accesses segment data for each objective, and depending on the data freshness or staleness, it may calculate or update expected values for the segments of the potential routes for the different objectives that we want to optimize by. Then, the stationary agent will normalize the values for each of these segments. It will calculate the cost per segment using the weighted objective function, which in the case of 3 objectives that are time, distance, and monetary cost, the cost of the segment would be the weight of the time multiplied by the normalized time, the weight of the distance multiplied by the normalized distance, and the weight of the cost multiplied by the normalized monetary cost. So the stationary agent will calculate the possible routes that the vehicle can take. As mentioned, the cost of each route will be the sum of the cost of its segments. The stationary agent bid will be the cost of the lowest route cost. And this will be the route that it would be recommending to the vehicle. So the vehicle selects and follows the initial segments of the lowest bid route. Then the process continues with replanning. As the vehicle moves, the vehicle reevaluates the options every few steps. Why? This happens because conditions can change. Like we can have congestion present that wasn't there before. We can have an accident or some other type of emergency can occur. So the stationary agents at the next step or some steps forward could potentially suggest better alternatives based on the new conditions. And this allows for real-time rerouting and self-adaptation. Let's see how the bid generation process would work for 3 objectives monitored. So we would require routes. We would query the database for the network segment data. We would get the segments for the different routes that we could take. We would estimate the expected traffic, vehicle speed for these segments of the road network. And then we would be creating our network graph using the distance, time, and cost in this case where we have these 3 objectives. And the weights would be according to the profile provided. We can use some algorithm to figure out which one of the potential routes would be the optimal. It would be Dijkstra, or it would be some other more sophisticated potentially. And then we would see if the route exists. Then we would calculate the bid and send it to the vehicle. If it doesn't exist, then we would send some negative value. and then the vehicle would select the lowest positive value that we could get as a bid. And let's see what happens next. So we said a route exists. If it doesn't exist, we cannot go to the place we wanted, so there's nothing to do. If a route does exist, then we receive a list of the next nodes that we need to go through, and then we start our journey and we see, is the next node congested, or is the list of the next nodes complete after this one? If not, then we move to the next node, and then we check if the next node is our target node or not. If it is a target node, we reach our destination. Yay, everyone is happy. If not, then we move to the next node after that, and then we check again. Is our node list complete? Have we been through all of them? Or is there some type of emergency or congestion in the next node? If there is some emergency or congestion or the list is not complete, we initiate an auction again. And then the process continues until we finally reach our destination. Here's a conceptual diagram of how this would work. You can see vehicle agents. You can see different type of mobile agents like the vehicles, emergency vehicles, public transport, and so on. And you also see the stationary agents. We do collect real-time traffic data, and it can be that stationary agents can also exchange data in case it will improve their estimations for the values that they will provide for the different objectives. So what I did was try to run some simulations to see how effective such a system would be. So I used the NetLogo simulation environment. I ran lots of simulations, a few hundreds, with different scenarios that included cases where there was congestion, emergencies, different type of vehicles. And this happened for some fixed distance. And this is the result I got. So for the same distance, I compared 3 different approaches. One is this normal routing, distance-based. You try to find the route with the minimum distance, and then you execute that. Same thing, you try to execute the route you found, this time using a multi-objective routing, so you can optimize for different objectives. But once you decide on some route initially, then you execute it to the end. And then the third approach is the Amor approach, where you do optimize for different objectives, but you do dynamic replanning every some loads, or as discussed, when there's some type of change like an emergency or congestion that wasn't present before. What we see is that the cost, monetary cost, when you have the multi-objective approaches, the dynamic and non-dynamic replanning, is more or less the same, but it is lower than planning a route based on distance only. And then we have a shorter travel time using multi-objective optimization than we would have optimizing based on distance. And we have even shorter duration of the travel when we do dynamic replanning with the Amor system. And we can finally see that there's really a huge difference in how much our trip duration would increase if we suddenly get congestion in the traffic. So there is some slight difference between the distance-based approach and the multi-objective approach, but Amor with dynamic replanning is really shining there with less than 20% of the increase compared to the other methods. That's all very nice. What would we need to actually realize this in our roads? First, we would need V2X enabled infrastructure. For those that are not familiar with V2X, it means vehicle to anything, and it allows vehicles to communicate with each other with different traffic elements like smart traffic lights or smart traffic signs, which can adapt what they display. And even with mobile phones, potentially, so the vehicle could communicate with the pedestrian that comes behind the building in the next block. So you could really see and understand how the environment around you is. Besides the smart traffic lights and the adaptive road signs, we would also have the roadside units, which would be the stationary agents. So from the vehicle side, vehicles would obviously need to be VTX capable, and the vehicles would be running the actual app, the agents that they would use in order to do their smart road planning and communicate with the rest of the infrastructure. On the cloud and edge layer level, we would need local road terminals. This would enable fast computation. And assuming we want to have some centralized overview of the traffic and potentially use this to do more centralized planning, we would need a city traffic management center. What assumptions are we making? So we're making the assumption that the map of the environment is known. So the vehicles do not do continuous and online localization and mapping. They know the map of their environment already. The road segments may have tolls or different charges. We do have available historical traffic data, and we continuously collect, as the system is online, additional ones. And the vehicles know their global position. Okay. We talked about everything, but the benefit, what would we gain out of this? We have seen a few things based on the simulation results, and this allows us to estimate that this would make it easier to optimize traffic flow. V2X enabled traffic signs and lights also play a role in this because you can change the signal timings based on the traffic and reduce the delays. AI-driven systems that analyze in real time the traffic data play an important role in enabling this. This would also help us reduce bottlenecks, both because we would try to optimize traffic flow, but we would also potentially redirect traffic through different routes that would enable them to have a smoother journey and less congestion. And all of this would lead to shorter travel times, which in our current environment in our urban cities would make a big difference for a lot of people that have to travel for a significant amount of time, spend some time on the road. They could spend it in something potentially much more pleasant and productive. Besides this, using the AI-driven traffic management system, we could have improvements with respect to road safety or how we prioritize our traffic. For example, when we have real-time road closures, something happens, we can reroute our traffic. Smart systems will enable us to do this in a faster way, and this will optimize traffic flow, and this would also help reduce potential accidents when there is a road blockage. We could also manage traffic in a priority-based way, so we can dynamically prioritize different actors and like public transport or emergency services. And in the case of an emergency, we could even help ambulances negotiate some green wave access so they get priority and they can go fast where they need to be. And finally, there are also environmental benefits and reduced emissions. We have a smoother traffic flow. This leads to reduced congestion, but also we don't have this stop and go traffic all the time as the traffic is smoother. And this enables vehicles to consume less energy, emit less CO2, and this also improves the air quality in our city. Thank you very much. Please share also your thoughts, your views, or how you envision traffic management in the future. Thank you.